So let's do a simple example. We've got a block being pushed up an inclined plane. And should we start? Let's make it frictionless at first. So we've got F push being applied to our block, and it's moving up from point A to point B. And I guess we could call that theta, and I guess we could just call this D. Okay. So first, why don't we do it using the, the Chapter 7 method, where we look at all the work done and say the work done equals a change in kinetic energy. So let's say that this thing started out at rest, and we were trying to figure out the final speed as it moves up the incline. You want numbers? Okay, I think this will work. All right, so the work method. So we'll draw a free body diagram. For the block. Go ahead and do that. Is that right? What's touching the block? The surface. Surface can interact in two ways, through a normal force, which we indicate here, and through friction, but our surface is frictionless. The hand, the push, touching the block. Those are the only things that are touching it. What can reach in from a distance? Gravity. So I broke up gravity into X and Y components where my coordinate system is aligned with my incline. All right. Yeah, these are weight. Yeah. What should I do? mg sub y? You like that better? The y component of the weight? Or you want me to just write it as mg? This one is going to be cosine theta, right? And this one is going to be... Is that better? Okay, so once we've got our free body diagram, we're going to find the work done by each of those forces on the block. Normal force, let's start with the easy one. 0. Because it's the normal force, right, times the distance times the cosine of 90 degrees, right? Work done by the pushing force. What is it? It's the pushing force multiplied by the distance d multiplied by cosine of 0, right? And what is the pushing force? 40 newtons times 1.2 meters? What is that, 48? 48 joules. Work done by gravity. Two ways to think of that. You can just, I've already broken up my gravity into two components here, right? So the component that's normal to the surface, mg cosine theta, that does no work. The component that's parallel to the surface is doing work, mg sine theta. Or you could have just left it as mg, and you'd have a different angle in there, right? That's okay too. So let's just go, I'm going to use my component here, mg sine theta times the distance times what? Cosine 180. So I get a negative mg sine theta times d. What does all that work out to be? 50. It's about 25. It's about 30. Roughly 30. What is it? Negative what? 50. mg is about 50, right? And then you're multiplying by sine of 30 degrees. Then that makes it about 25. Yeah, that can't be right. Then you're multiplying by 1.2. That makes it about 30. And the third step, we say the total or the net work done is equal to the change in kinetic energy. So what is the net work done? It's the work done by the normal force plus the work done by the pushing force plus the work done by gravity. Change in kinetic energy is the final kinetic energy minus the initial kinetic energy. And we know the initial, in this case, was 0. Then we just put these in here. We've got the 0 plus 48 minus 29.4 is 1/2 m v final squared. And so now we can solve for v final squared. What do we get for v final? 2.73 meters per second. Sounds about right. Okay, that was the work method, right? The chapter 7 method. Find the work done by every force. Work equals change in kinetic energy. The net work, the total work done on our block equals the change in kinetic energy of our block. And we find out v final or whatever we're looking for.